in. And these subsidence rates are much faster than typical subsidence rates published for passive margins for fallen basins. They are possibly comparable with strike-slip basins, but they don't have the fault control required for them to be strike-slip basins. So here's an example of the Patney Basin with its synformal geometry, thick section down to 5 seconds here, with only minor faults affecting it. They're very numerous, but they're minor. So one model that I developed with Rob Westerway for these basins was, we've got a basin that's formed here, and we need some sort of trigger, could be a climate change or some tectonic change, and we get an uplift in the source region. That supplies sediment to this area. And then just like loading of a salt basin, in a way, this creates a pressure here, resulting in flow of the lower crust, and that flow goes to the sediment source area. And so you end up with a virtuous cycle here of lower crustal flow here, uplift in erosion, sediment returning to the basin, and we get this rapid subsidence that accommodates as much sediment as can be thrown at this area. And Peter Clift and Sascha Bruun took this model and applied it to the Bayern sag. So in the past, I think I've already answered this question: is deformation in mainland Southeast Asia dominated by the effects of Southeast Asia? It used to be thought that it was, but from what I've just said, hopefully you will think that no, it's not. There are two end-member models for this. One is the escape tectonics model, Molnar and Tapane, 1974, and has been developed up until more recent times. This analog model would not get published today. It's unscaled. There was a glass plate put on top to stop the Himalayas developing so that this would develop. But it does provide an illustration of what escape tectonics might do. And then there's the more continuum of a deforming solid model proposed by England and Molnar and Shen et al. And the continuum model is supported by the GPS data that shows generally gradual changes in modern velocities around Southeast Asia. But there are areas, particularly the Sagaing Fault, where we do see rapid displacement focused on a narrow fault zone. So let's just take a look at this area first, the Andaman Sea. This is gravity data and calculating crustal thicknesses from the CSAT data. And we see here these hyperextended crustal areas here, the spreading center here, and quite thin crust, but going up to 30 kilometers here. We'll come back to that area in a moment. First of all, I want to mention this model by Westerweel et al. 2019. They conducted extensive paleomagnetic data in the Wunto area and here. To date, movement of the West Burma block, or the Burma block, and what its paleolatitudes were during the late Cretaceous and Eocene. And they found that it should be 5 degrees south in the late Cretaceous and about 4 degrees north in the late Eocene, which means a remarkable amount of translation, creates all manner of problems for explaining how you lose the crust between this and this area here without a major collision being apparent here. Seems to require strike-slip translation to mitigate the absence of a collision. So we can take this model, early Eocene to Pliocene here, and say, well, how does it fit the basins that we were just looking at in this area in the Andaman Sea? How does it fit the subduction zone development here? There is another question. So if we just look at this area here, what we see in the basin, this is a map of the base of the Sin Rift. We have a large strike-slip fault here, the Mergui High here, rift basins sitting back here. Very nice transtensional fault pattern developed here, indicating north-northwest, south-southeast extension. Fits a strike-slip transtensional model quite well. In a cross-section through this basin, we see that's quite well developed, probably Oligocene to Miocene section. The rifting stops in the middle Miocene. And there's some seismic data through here. We have a 3D seismic data section in Thailand. This is the Moho. This is the base of the sedimentary section. The problem in this area is we know the crust thinned to about 5-6 kilometers. It's heavily intruded. There's fabric in here that is probably a stretching fabric, a ductile stretching fabric. But where is the Sin Rift section? We see a later section sitting on top, but we seem to be missing the phase that actually caused the thinning. And I suggest to explain this, what happened is we have a detachment fault sitting in here. This removed this part of the crust to the seawall rise, which is sitting in here. What we're looking at here is exposed lower crust below a detachment. And then we have this Miocene section deposited directly on that. And then the strike-slip deformation comes after that. But this is all an entirely extensional scenario. And it just does not fit at all well with the paleomagnetic data that requires the West Burma block to come in through this area. And I don't have a solution for this, but it's a common problem. Paleomagnetic data in the region is very important for the Borneo rotation, but there's models for this that are uncertain. Did it rotate in the Paleogene, or did it rotate the anti-clockwise rotation? Was it predominantly in the Neogene? The degree of Indochina rotation in response to and extrusion in response to escape tectonics is controversial. Then the Burma terrain. So the paleomagnetic data is key to the plate reconstructions, but it's all to some degree controversial and still unresolved. So for the escape tectonics model, the Red River Fault displacement here, Leloo published a very significant paper on this, where he talked about the localization of deformation that continued for tens of millions of years, that absorbed a substantial part of Asian Cenozoic shortening, that the strike-slip faults sliced the entire lithosphere. They may have led to opening of the South China Sea. The lateral offset has been proposed between 500 to possibly 1,000 kilometers that occur between 36 and 16 million years. And so that's their published model. And you'll notice that the Mei-Ping fault here goes all the way over to northwest Borneo, to the fault thrust belt here. And there's no Proto-South China Sea in this model. The model for strike slip produced the first explanations for the rift basins in the Gulf of Thailand. Taponnier explained it under sinistral deformation. Polar-Chan explained it under dextral deformation. And one of the problems is during the lifetime of these basins is when motion switched from sinistral to dextral. So you can't really have it both ways in these basins. They can't be developed under sinistral and dextral deformation, both opening under extension. So there are inconsistencies with this model. Another issue with these faults is determining the magnitude of strike slip deformation. We can look at the intensity of deformation within the shear zone and get some idea of the likely magnitude. At least, was it kilometers or tens of kilometers? Offset of geological markers would be good, but they're rarely reliable. Offset drainage is good for smaller fault systems. Paleomagnetic data has been used, but that's controversial. Slip rate and duration of faulting is useful for faults like the Sagaing fault, but how far you can project the slip rates back in time is debatable.